Moving to our next speaker, the mobile robotics the industry has been working on developing dynamic systems. It is interesting that the mechanistic knight was developed by Leonardo da Vinci in 15th century. What do the experts in this area are doing right now? Well, Gonzalo Ferrer will expand on that. Your applauses. The head of the mobile robotics lab of Skoltech, Gonzalo Ferrer Minguez, is going to talk about robotic navigations, the navigations for robots.
Hello, everyone. Yes, now we have the presentation. My name is Gonzalo. I will talk today about my personal journey on robot navigation. So this is a research journey that started 15 years ago, and I want to share this with you. I'm personally associate professor at Skoltech. So if you haven't heard about our university, we have like this campus in Moscow. Okay, and basically our objective is to do research and to train next generation of scientists and technology leaders. About my laboratory, I'm heading the mobile robotics laboratory. Here we have some students, some engineers, master students, and we have two main goals. Okay, so we work with robots, but we're interested in these two questions. The first one is robot perception, how we can use the sensors from a robot to perceive and understand the world. And the second question, this is the one that I will be talking more today. It's about how to actuate in the world. So this is about robot navigation. You have some task, and you want to achieve success on this task with the robot in this real situation. Okay, so the timeline of social robot navigation looks like this. I started working some years ago. I will present each of the methods. And what I want you to see is the evolution of these methods. Okay, so we will start talking about simple methods that are very efficient. And finally, I want to talk about what are the current directions from research. What is the current bottlenecks that are ahead of us? Okay, so let me start with this first method that we investigated. This is the social force model. This method is from neuroscience, but we borrowed for robotics. Okay? The idea is very simple. Every agent, it could be person, it could be also robot, is just a point where some external forces are actuating. Okay? After summating these forces, so for instance, there could be, well, some objects, like other people, maybe other robot. Each of them is exerting a force to the agent, and as a result, you generate a trajectory. Okay? We know this is not exactly accurate how reality works, but it's a good model to start. So, well, we tried this. Here you can see, like, this is old video that it was recorded in Barcelona, UPC. Yes, now it's playing. So we are here observing like some obstacles, some other people getting on the way, and basically we see how the robot is navigating on these very simple principles of looking at close objects and reacting to them. Okay, so this model was very successful. Okay, it's very efficient. It's capturing people surrounding the environment. So this is something important, right? Because you need to capture the social interactions. The problems, the limitations, and have in mind that this is already almost 15 years old, is that it doesn't behave well enough in complex scenes. So when there's many obstacles there, where there's more people, it's not really solving the problem correctly. Okay, it's not navigating correctly. It also requires very good perception. So this is the other part I will talk about. Basically, you want to detect people, you want to detect the obstacles, and for this solution that I was showing, it's a simplified version of real perception. Okay? So then we move on. What we thought is we want to do this system a little bit more complex that can handle more difficult situations. So for this, we studied what we call the multi-policy decision making. It's a simple algorithm where, in essence, what you are doing is choosing between very simple behaviors. Okay? In these examples that I'm showing, we have 3 different behaviors. You can go solo. So this is similar to the previous method that I was showing. You just forward and try to reach a goal. You can stop. Okay? So this policy might look trivial, but actually it's very important. All the time you're just trying to stop because there might be unexpected events. And you can also follow an agent. Okay? Each of them is an individual policy. And what is the interesting result about this is that there's an emergent behavior that raises from combining this. Okay? So the algorithm is just choosing what policy to execute, but with this you can get very impressive results. Okay? So let me play like this video. This was recorded in University of Michigan also some years ago. Okay, and what we can see is that this simple behavior actually results in trajectories that we can thought as more intelligent by the robot. Okay, so it's stopping, it's reacting, lowering its velocity, it's doing all these maneuvers just with 3 simple policies. Okay, so in this example, we were trying to be adversarial to the robot, creating examples where complicated to solve. Okay, so mostly the robot needs to avoid collisions, and we were just getting on the way. But the results of this are performing well. Okay, so for instance, we have an example. This pedestrian starts running. Okay, and we are able to foresee that there will be a collision, so the robot needs to stop. Okay, so there's also like examples, clutter, the robot cannot really progress on this. Well, this is details, but at the end, what I want you to think about is that this is 3 simple policies that we are combining together, and then the algorithm behaves very well. Okay, as I said, the advantages is computational efficiency, and the second one is that we are capturing risk. Okay, and I will elaborate more on risk later, but it's basically all these situations that could result in a collision. Okay, so collision is something we don't want. Imagine this is a small robot, but this kind of algorithm could be applied to larger vehicles or other kind of platforms. So collision is not acceptable for pedestrians or for other objects. And yeah, so kind of the negative part of this is that we are just choosing a policy, but we are not explicitly avoiding collisions. Okay, so we don't have this as a constraint, and this is a problem because depending on the configuration, you are just going to choose a policy that might result in collision. Okay, and it also requires good perception. So we have the same problem again. We need to perceive the world, and we need to understand if the pedestrian is there, if this is the same pedestrian, if it has this velocity and all these problems that in real world they are more complicated than in this simple example that I was showing. Okay, so we continued a little bit our development, our journey. So now we are just some years ago. And then we start looking at this solution of we want to incorporate risk into our plans. Okay, so for this, we can explicitly add an objective, and we are just going to be optimizing over this. Okay, we can also add this as a constraint. And well, this constraint could be probabilistic, could be deterministic, but the idea is that now the solution will take into account these constraints. If there's a collision, we should be avoiding after solving this problem. Okay, we did this in 2 stages. First of all, on simulation environment, here we can collect data. No pedestrian will be harmed in simulations, so even if there's collisions, we can run more simulations. And we have a second stage, which is the real environment. Okay, so in this case, we will have a robot, and this robot is going to also navigate among people, and we want to ensure that this risk is minimized. Risk of collision, I mean. Okay, so we have here some experiments. Here, this is new robot that we have in Skoltech. We were doing like some experiments of navigating among pedestrians. And well, basically the objective of the robot was to achieve just this goal without collisions. Okay, so it looks similar, but under the hood, the difference on the algorithm is this. So we are now explicitly looking for collisions, and we are avoiding this. Okay, this is another video where we have like more pedestrians working adversarially. Okay, so they are kind of getting on the way, and we need to solve the problem for navigation. Okay, so this is a little bit the timeline. I have simplified things a lot. I have just included kind of the highlights with results on videos and qualitative data. But you see the trend, okay? So we started, some time ago with this social force model, a reactive model that was very simple, but was capable of performing well. This could be improved with the MPDM, right? So this is just combining different policies. And finally, we were taking into account risk. Okay? Now the question is, if we have a control environment, we know that robot navigation can work very well. But lately, the question is, we want to have a better navigation policy, and at the same time, we want to perform anywhere. Okay? And this is a fundamental task because it requires to improve the perception system that we have here. So most of our efforts now on research are in these two directions. Okay? So we want better navigation policies that are more robust. We can get very good navigation results, as you see on the video, but they need to be robust to any kind of environment. For instance, here, with these lighting conditions, a lot of people, other objects, will want our robot to be able to navigate in environments like this. Okay, so let's start with kind of, everyone, I guess, will talk about this one way or another. We have foundation models, okay, for language and for vision as well. They are changing the landscape in many topics, in many disciplines, so robotics is also one of them. Okay, they have been trained with large amounts of data, and using them actually makes all this perception more robust. Okay, it doesn't make it perfect. You will see that we need to adapt this to our needs on robotics, but it basically gives us now tools to be used that before were not available. Okay, they were not reliable enough. So for instance, multimodality, very important. We've been investigating visual information matters, comes from cameras, and it gives you a lot of information, but it's not the only source of information, okay? Maybe text, language could be like important modality to understand how we want to navigate. Maybe audio, maybe depth, okay? Different modalities will make the policy more robust. Okay, this is something we're investigating. And then perception, okay? So this is the problem I was saying before. If you don't detect correctly an obstacle, you don't detect correctly a person, you could be having an undesired collision, okay? So one way to improve perception is just providing unified semantics on the environment. So what is this? What do I mean by this? So we have a map of the environment, okay? It could be like a 3D representation like here. And what we want is for each of these regions, each of these objects to be detected and also to say to what category they belong. Okay, so for instance, in this example, we see some pictures that are observed here, okay, in this bottom picture. We also see the semantic classes, like for instance, wall, or floor, or other larger areas on this scene. and we want to combine all of it together. Okay? And that's one limitation about it. Okay? What is exactly these labels that we are going to use? What is these objects, right? It could be very detailed. You could be saying, look, there's 3 kinds of chairs. One of them is like color beige, the other is black. This one has these properties, other properties. There's a lot of metadata on top of these objects, right? While on the other hand, let's say that fixed labels just classify them as the same object, okay? This matters, for instance, if we are interested in people, we're interested in different objects that could be in the scene, and they can interact somehow with the robot, okay? So either by navigation or other tasks, we want to make this distinction. The problem is that these categories could be very unstable, okay? What I mean by this. So in this example, we see table, okay? This is just the same view, but they are classified as different objects, okay? So one of them is saying that this is a table, the other is saying that you have a small dining table, and the other result, just few seconds later or milliseconds later, is telling you that this is a wooden table. Okay, and the question is, but maybe for our task, we just want to have tables that are general. Okay, so we need a way to unify semantics. The foundation models gives you like very strong tools to detect any kind of objects, to extract information, and get labels or other kind of description of the object. But for the map and for other tasks, you might want to unify these semantics. Okay? You cannot have infinite number of classes because you have just observed the same scene just a little bit later. And a little bit later, you get another output. Okay? So this is not good for stability. So what we could do is provide a unified semantic map where it's taking all this into consideration. So for instance, you could have like tasks that are show me the table, or maybe show the wooden table, or show me the small table, and we refer to the same object because we know this has been unified into the same category. Okay? So I think for robots that's important. Foundation models provide you like this tool that allows you to have very precise description, but you want to reduce this, not noise, but let's say variance on what the labels are. You want to get things consistent because, for instance, when you want to do maps, if you don't have the consistent label, you can have errors when you are building the map. Okay, imagine you are seeing now a table, then a wooden table. Are they different? Are not the same? So the system will be a little bit confused. This is a scheme of the general view. Okay, so we do mapping, and on top of the mapping, we are just projecting labels. And well, there's this unified process that is happening here, okay, at the bottom. But I just want to show the idea because that is about this. This is the unified, you need to unify the semantics. And for instance, this is the result of unifying versus just having open vocabulary with any kind of object that you see. Okay, so I'm going to play it. Well, it's going to play again, I think. Okay, so you see how the open vocabulary is not so consistent in the objects. You see like some of these chairs having like different categories. We don't know exactly what they are, but on the, let me play it again. On the right, you see like colors that are green and red, okay, but on the left, after you have unified semantics, you have kind of the same object, okay? So maybe when you want to run task, even though that the map can be correct, this kind of example could confuse the robot policy, okay? So for instance, one is like 2 kind of objects, like blue seat and blue chair, while the other is just unifying them. Okay, so a little bit more qualitative results. So this is more about mapping. What is the quality of the mapping that you are getting in here? Unifying versus not unifying. But at the end, have in mind that what we want is to execute robot task. And for this, we need to improve perception, okay? So now, the advantage is that we can get out and have like open vocabulary, but at the same time, this is a limitation, okay? So this is how we are solving it, providing this unified view. So what lies ahead robot navigation? I described at the beginning like many models, okay, that are very simple, they are very efficient, okay, and they work very well in control environments, mostly when we have good perception. From there, we saw that the navigation was performing very well, but the challenges were on how to transition to more complex environments, right? Like real scenes. Like imagine this conference today would be very challenging for robot. For this, we have two ongoing research directions. So one is looking at multimodality, especially with images and text, okay? Because what we want is to have more robust policies. And the second is to improve the perception to have also more robust perception, okay? So I think this is the key word that I want to say on this presentation. We want more robustness when we deal with real-world deployment of robots, okay? And the second that is also connected is risk, okay? Most of the examples of collisions are because usually there's a problem on the perception. Okay, so we want to handle this correctly. The only way is not really by improving the policies, as I was showing before, it's also by improving the perception and taking this into account on the robot policy. Okay, so this is like proper end-to-end risk assessment on the system that for us, I think this is like very interesting condition. And it only happens the moment that you get out into non-control environment, like the street or this environment, okay? That is when things start getting more complicated because maybe there's objects or parts of the region that we don't really understand well. Even the foundation models don't give us like clear answer consistently, okay? So how is this relevant? Okay, so if we want this new generation of robots to be deployed more reliably, we need to solve this problem. So this is the research direction that my lab is now working on. I also provided like this view on how this has evolved over the time, and well, I hope that everything was fine, and maybe there's some questions I can take, or if not, I will thank you for listening. Thank you.
Thank you, Gonzalo Ferrer. Applause to the speaker. Thank you for this very interesting performance. Thank you very much.